Hello and welcome to a short video on bidirectional encoder representations from transformers, the BERT embedding. If I say that BERT embedding basically has revolutionized the field of NLP just recently, I would not be wrong. This BERT algorithm or BERT embedding, basically it appears from Google AI, the research from Google AI, and it actually outperformed all the existing embeddings with a lot of distinctions. Several distinctions are there. First, they have used bidirectional, deep bidirectional recurrent neural networks. They have given, for example, self-attention layers. They have actually gained the benefits from transformers, which are much more efficient than LSTMs, traditional LSTMs. And the way they actually built this BERT actually has several kind of superseding distinctions over the other models. For example, the existing model like famous embedding like word-to-vec or glove, or maybe the negative sampling, they work very well. But the problem with those is they don't are context aware. What I really mean about that is, for example, if you have a sentence, for example, this is my bank account, let's say, on the river bank, let's say. So the traditional embeddings, for example, word-to-vec embedding, that is word-level embedding, word-level feature extractor, it may assign this word bank the same embedding as this bank, although the both have different context, and based on their context, the embeddings, they should be really different. And this context-aware embedding that actually gives the features, gives the embeddings so distinction as compared to the other embeddings that recently it actually has just supersede or outperformed all the existing embeddings in several different tasks. For example, whether it is a text classification task, BERT embeddings are used there. They are pre-trained embeddings on very large corpus of data. And actually it's an unlabeled data. That is also a distinction of BERT. It is not trained on a labeled or a supervised data set. That's completely an unlabeled data on which it is trained. And after having all this kind of training, it actually has distinction between this context awareness as compared to glove or word-to-vec and all the existing these kind of embeddings. And also, what they actually went through is they deployed a masked language model, which actually worked like the following. So they went through, for example, a very large corpus of data set, and they learned this embedding using masked language model in a following way. So for example, given a sentence, this is good, let's say, mask, I will eat it. So mask, again a mask. So they actually intentionally blank out or mask out some of the words, although they know what the original word is in the text, and they train their model to actually predict these kind of words, the masked words. For example, here this might be a meal, the word, and here this might be eat. So by masking several words, they actually trained a language model that actually was very good in predicting these blank words. One source of information here, if the masking of the words, they have used actually the 15% masking. If the masking of the word is too small, if you are using too small masking, then actually the training will become much more expensive. And if you will be using a lot of masking, a lot of blanks, then you will be losing a lot of context. So the percentage of masking is really a hyperparameter, but in the very first step, what they do is they mask some of the words out of the corpus and train their model to actually predict these kind of masked words. And with that, they actually go on, and the second technique they have used is next sentence prediction. So what they really do is, that is kind of a binary classifier. What they actually do is they actually give, in the model, they actually give the pair of sentences, so sentence A, sentence B, and if sentence B follows from sentence A, it is the next sentence from A, then the output is 1, otherwise the output is 0. So that's a binary classifier that they actually come up with. So in masked language model, for example, the output was a softmax, the softmax unit, or the vector of probabilities for the prediction of masked word, and that actually the dimension of the output word in terms of the softmax layer is the total number of words in the vocabulary. Here, that's a binary classifier. And after training this masked language model and the next sentence prediction with the help of transformers and with the help of, for example, these self-attention layers, multi-headed self-attention layer, they came up with, and by the way, all this training is done on unlabeled data. There is no label data, there is no supervised label data. They just went through a large amount of corpus of data, and both of these corpus of data, they can be trained using this unlabeled data. You need not to have any labels. For example, the masking the words, you already know what is the word there. Originally it was there. And the next sentence prediction, you just go through the data and you see which pair of sentences they follow each other, and you can just build this model based on completely unlabeled data, and that's remarkable. Further, replacing this LSTM with transformers and self-attention models give a lot of parallelism, distribution, and great efficiency they actually came to achieve. So once they came up with this BERT embedding, actually now this is a word level embedding. Now you can use this embedding, for example, for any kind of NLP task, for example, text classification. You can use it, for example, a question answer session, machine translation, I mean anything. That's an embedding like the other embedding. But this particular embedding is much more powerful than, actually empirically it's much more powerful than the existing embeddings. So with that, let me just show you how you can compute this kind of embedding in Python. Let me just give you a quick overview of BERT embedding that is there. You have to install BERT embedding package. So for example, you can write pip let me increase the font size here. Pip install BERT embedding, and you just, on your console, you just press enter, and it will install the BERT embedding package, and from there you can use this BERT embedding. So because I have already installed this package, so I'm going to use it. I'm going to show you how you can use that. So from BERT embedding, import BERT embedding. Yeah, so it has already been installed. So let me make some sentences, and we will see how this embedding works. So first of all, I have to make certain sentences. Let's say sentences is, let's say, a list of sentences. Let's say this is my bank account, and then the second might be, it is on the bank of a river, let's say. So these are, let's say, two sentences. And what I can do is this BERT, pre-trained BERT model for transfer learning, or maybe for example, fine tuning. It's available in different models. It's available in 1024 model with 24 layers, or it's available with 768 dimensions with 12 layers. So let me call the model with, so let's say BERT embedding model, BERT embedding layer, BERT embedding layer as, or layer or model, or I mean anything. Model is BERT embedding, and there you can set the model, which model you are interested in. So the two models are available to date. So let's say 24, 1024 and 16. So it will actually download this model, because I already have downloaded this model. So maybe it pick a cache copy on your machine for the very first time. It may take a couple of minutes to download this pre-trained model. Once you have this model, now you can compute the embeddings. So let's say embeddings or feature vectors, embeddings is equal to, let's say, BE model, and there you can give these sentences, and it should generate different kind of embeddings here. So let me show you the embeddings. So first of all, let's see the very first sentence. So first sentence is embeddings 0. That's our first sentence in tokenized form. If you see, oh, by the way, I should use the first sentence 0 for the sentence. This is my bank account. Now, in this first sentence 0, it is basically this thing. The first sentence 1, it actually generates it actually has the feature vectors for the first sentence for all the words. For this, it has a feature vector. It has a feature vector. That feature vector indeed is a BERT embedding. So let me pick, let's say, A1. And here you can see A1 has a shape, which is, A1 has a length, which is equal to the total number of words in our first sentence. Now you can, for example, pick A1, 0, and if you display that, that will be a bunch of numbers. And if you see how many are these, you can just see 0.shape. And that will be the, there are 1024 dimensional vector BERT embedding for the word this. Similarly, we can have the same dimensional embedding for the word is. So A1, 1.shape. So that is for is. The important thing is, if you see the embedding of this word bank in the first sentence, which is at the index starts from 0, it is at 3, and the embedding for the second the embedding of the bank for the second sentence, it will be different. For example, bank sentence 1, bank 1, that is A1 at index 3. That is embedding for sentence 1. Similarly, if you go to sentence 2, second sentence, that is FS1, and there you can pick, for example, SS0. That actually gives the second sentence. What is that? FS, is this FS? Oh, embedding. I should go to embeddings. So that is SS. If you go to this is basically the sentence in a tokenized form. Here we have 0, 1, 2, 3, and 4. The bank is at 4. So what we can really do is SS1, and from there we can pick the fourth one. So 0, 1, 2, 3, and 4, and that is basically bank 2. So now if you see bank 1 and bank 2, they might be different. For example, bank 1, let me display 5 values of these, and we can see bank 2, let me display just 5 values of these, and you might be seeing there's a significant difference in the feature vector, the first 5 values in the feature vector of bank 1 as well as the bank 2. So for example, if you see this is negative, here you have positive. So it actually generates the embedding for the word bank in 2 different contexts. The embeddings are completely different. So now once you have embedding of your sentences, word embeddings, now you can apply any, for example, recurrent neural network on top of it to apply a text classification or machine translation, or I mean, all the tasks that you can do with other kind of embeddings you can do here as well. But it just turns out that this BERT embedding is context aware. It is really outperforming the other embeddings. So it basically should be used, or it is basically recommended to use BERT embedding for NLP tasks. It is like so people say it is like for computer vision or convolutional neural network, the goal that was done by ImageNet, that is the same goal is done by BERT for NLP. So with that comment, I end this video here. I hope you have enjoyed this video. Please press the like button and subscribe our channel, and share this video among your fellows. Hope to see you next time.